All right, so let's look at another example for solving rational equations. This one's a little more involved, but that's okay. We can just take it step by step. If I want to find an LCD, I think I'm going to try to factor these denominators first to see what they might be, right? So this first one here, if I have 2s plus 6, I can factor out a 2, and I get s plus 3. The second one, if I have 5s plus 5, I can factor out a 5, and I get s plus 1. And then I've got 10s squared plus 40s plus 10. And no, a isn't equal to 1, but remember we always check for GCFs first, and it looks like it shares a 10. So this is going to be 10s squared plus 4s plus 30. And now, ooh, I've got a is equal to 1, two things that multiply to 3, add to 4. So 10s plus 1 and s plus 3. So between these three, it looks like I've got an LCD, right, of 2 times 5 times s plus 3 times s plus 1, right? 2 times 5 gives me the same 10 that I have here on the right. S plus 3, s plus 1. So yeah, I think my LCD is 2 times 5 times s plus 3 times s plus 1. Or I can just say it's 10, right? S plus 3, s plus 1. And remember, multiplication is commutative, so 10s plus 1, s plus 3 is the same as 10s plus 3, s plus 1. But this is something, and I kind of alluded to this before, we also are going to see that we have a domain restriction, right? So I can't divide by 0. So that means for our rational, when we're doing rational equations, and we'll even talk about this with rational functions, we're going to have some domain restrictions because we can't divide by 0. So we're going to set that LCD equal to 0. So 10s plus 3, s plus 1 equal to 0. So using our zero factor property, right, s plus 3 cannot equal 0, s plus 1 cannot equal to 0. So s cannot equal to negative 3, or s cannot equal to negative 1. So we kind of have those restrictions that we can imply from the get-go here. And then we'll also kind of see as we solve that maybe we're going to be able to eliminate one of those solutions if one of them happens to be negative 3 or negative 1. All right, so now once we have this, we can actually just multiply through like we've done before, multiply by the LCD, cancel factors, and then simplify and solve. All right, so if we use our LCD here, I'm going to multiply both sides of this equation by that. So I'm going to have 10 s plus 1, s plus 3, times s over 2 s plus 3 minus 10 s plus 1 s plus 3 times s over 5 times s plus 1. So we're using that factored form that we came up with, equals 10 s plus 1 s plus 3 times 5s squared minus 5s minus 7, all divided by my 10 s plus 1 and s plus 3. So now let's cancel common factors before we go to the next step. First piece here, let's see on the far left here, I've got a 10 and a 2. Those share a factor of 2, so I'm going to get a 5 and a 1. S plus 3, so 1 and 1. So this is going to simplify to 5 s plus 1 times s minus, see, 10 and 5 share a factor of 5, so I've got a 2. S plus 1 are going to cancel. I'm left with an s plus 3 and an s equals, and then on the right here I've got 10 and 10, that's a 1 and 1. S plus 1, s plus 1, s plus 3, s plus 3. So I'm left with 5s squared minus 3s minus 7. And it looks like now we've got a quadratic that we're going to have to solve. But let's simplify this. So on the left, we end up with, what, 5s plus 5 times s minus 2s plus 6 times s equals 5s squared minus 3s plus 7. So I start by distributing my 5 and my 2. Now I'm going to distribute again. So this is going to become 5s squared plus 5s minus, don't forget the minus goes to everything, right? So minus 2s squared minus 6s equals 5s squared minus 3s minus 7. And then because this seems like it's a quadratic, You can kind of collect like terms and simplify, but on the left I have 3s squared minus s equals 5s squared minus 3s minus 7. And then remember that when we solve quadratics, we have to set everything to 0, right? So I'm going to move everything over to my left side. 3s squared minus 5s squared. We're going to subtract this 3s. We're going to subtract this 7. So we're going to add there. Right? So I've got 3s squared minus 5s squared minus 2s squared, negative s plus 3s, so plus 2s, and then plus 7 is equal to 0. All right, and now we can try to factor this, or I don't know, why don't we try the quadratic formula? I think that might be a little bit easier here, especially since I've got this negative, and I'm not thinking that this is going to be factorable. So let's review our quadratic equation here, right? So x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So my a is negative 2, my b is 2, my c is 7. So x equals negative 2 plus or minus 2 squared minus 4 times a times c, all divided by 2a. So x is going to equal negative 2 plus or minus the square root of 2 squared, so 4, 4, 7, 2, 56, right? So this is going to be 4 plus 56 over negative 4. So x is going to equal negative 2 plus or minus the square root of 60 over negative 4. And then remember that we can actually continue with this and simplify this further. All right, so let's go ahead and apply our quadratic formula here. So this is going to be equal to negative 2 plus or minus, let's see, 60, square root of 60, perfect square in there I think is 4, right? 4 times 15, all divided by negative 4. So this is going to simplify to negative 2 plus or minus 2 root 15 over negative 4. And remember we kind of talked about that magic triangle, that if all three share a factor, we can simplify. They all share a factor of 2 there. So this is actually going to become x equals negative 1 plus or minus root 15 over negative 2. And so we can simplify this then a little bit further. So this is actually going to be x equals negative 1 minus root 15 over negative 2, or x equals negative 1 plus 15 over negative 2. And notice neither one of these are domain restrictions, right? We had a domain restriction at negative 1 and one at negative 3. Neither one of those, so we've got two solutions here. They just happen to be irrational solutions, but they're still valid solutions for this problem.